Welcome back, class. We are moving on in our unit of working within triangles, inside triangles, to learn all the wonder and magic that is there. So we finished up mid-segments of triangles last time. This time we're going to talk about perpendicular and angle bisectors once more. So what we're going to learn today is the perpendicular bisector theorem and the angle bisector theorem. We're going to use the perpendicular bisector theorem. We're going to use perpendicular bisectors and use the angle bisector theorem. This all sounds so much fun. And how do we start? Y'all know, with notes. All right, so the first note is about the perpendicular bisector theorem, which requires a little bit of background information, and I'll hook you up. It's all good. Some cool stuff goes on in these words. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Doesn't that make sense? Yes. Basically, if you have a perpendicular bisector on a segment, any point on that perpendicular bisector is equidistant from the end points. That's what that says. And the converse is, if a point is equidistant from endpoints of a segment, that point is on the perpendicular bisector of the segment. So this could be confusing because it's a lot of fun notes that we don't use these words every day, right? It's not everyday conversation. You talk about perpendicular bisector, especially if you talk about equidistant. Speaking of, what the heck is equidistant? So equidistant is exactly how it sounds, okay? Equi or equal, and then distant, having to do with a distance. So, same distance. That's what equidistant means, okay? It just means it has the same distance. Don't be afraid of that word, okay? It could be scary because it has a Q in it, and we don't normally say it in our everyday lives, but you can figure it out if you think about it and break it down a little bit. So anyway, that's the perpendicular bisector theorem. Now, to get more on that perpendicular bisector theorem, let's do some review. You remember constructions from like way, way long ago? And I know a lot of the students in my class are like, oh no! Yeah, so we're going to do constructions. So here's a given segment. And let's say we name the segment endpoints A and B. And what we're going to do now is construct a perpendicular bisector. I'm going to go kind of quick. So how did we construct a perpendicular bisector? Remember, we did stuff like this, and then we did, an arc way up there and an arc down there. Then we went to the other endpoint with the same measure. And I think I talked about in the video for this particular construction about how funky it is to work with your left hand. And so we have our two intersecting points here and here. So we have now constructed a perpendicular bisector, okay? Now what the perpendicular bisector theorem is, let's say we call this line line L, okay? What this does, right? What have we have done? We have now established, and let's call this little point in the middle point P. What we have now established by constructing that perpendicular bisector, we have now established that AP is congruent to BP, okay, or the distances are the same. So it's the first thing that we have done. We've established that those two are congruent. The next thing we have done is said, this is the bisector theorem now, any point on line L, no matter what point, let's say I pick a point way up here and call it like Z or something. If I pick any point there, that point is equidistant, same distance, equidistant from A and B. Okay, so that whole theorem, as intimidating as it is, okay, this is what it means. Okay, so we've constructed it in the past. We're just now breaking it down, and we have now done that. Okay, so it's equidistant, right? So that's what that means. And the same holds true for any other point, right? Pick another point, maybe something down here. We'll call that point Q. Why not? That is also equidistant from A and B. Okay, so it's like the sliding congruent thing going on, and hopefully you see why based on the last chapter. That's a hint, boys and girls. Based on the last chapter, you see why that's going to always be true. Because what will always be true, and we'll talk about it later, no matter where the point is on that line L, no matter where, we can have it under here too, no matter where that line is, or where that point is on line L, we are going to have congruent triangles no matter what, because of side, angle, side. Okay, so no matter where it is, we're going to have congruent triangles. So the distance will be the same because corresponding parts of congruent triangles are congruent. Full circle. Anyway, that's the whole note for perpendicular bisector theorem. But we're not done with bisectors because we've got angle bisectors as well. So we have the angle bisector theorem, okay? If a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. Holy cow. Now, we have again that word equidistant, okay? It means same distance. But what's going on? If we have an angle bisector, and any point on that angle bisector is going to be the same distance to each ray of the angle, okay? And we're going to talk more about that in a second. The converse of this theorem is that if you have a point that is equidistant from each ray of an angle, then that point is on the perpendicular, the angle bisector of that ray, or of that angle. So that's the angle bisector theorem. It's all about equidistant. Let's learn this a little bit better. I hope, anyway. That's the plan. And the way we're going to do that is some more review. Do you remember constructions? We're going to construct an angle bisector. So how did that work with the good old angle bisector? So you can review way back to Chapter 1, Tools of Geometry. But I'm going to do a quick angle bisector. And then we'll see some magic start to happen. I hope, anyway. I hope you think, wow, that's kind of, you know what, Mr. Katz? That's kind of cool. So we've constructed our angle bisector, or the ray that will definitely bisect the angle. Okay, so we have now made our angle bisector, and I got a few points. So that's the angle bisector. So we know these two angles are congruent. Okay, so that's the angle bisector by construction. Now, the bisector theorem talks about a distance on the ray. How in the world do we get a distance from a point to a line? What does that even mean? Okay, so there's a thing here that we kind of overlooked. Point equidistant from side. What in the world? How does that work? How can a point have a distance to a side, right? So we have to understand that fully. So we have to understand that the distance from a point to a line or a segment or a ray, a side basically, the distance from a point to a side, a line, a segment, or a ray, is the shortest possible distance. And guess what that makes? A right angle. So take, just for example, the point on the ray that we constructed. How far is this point to this side of the angle? Right? Is it this far? Is it this far? Is it this far? Right? It's the shortest distance, okay, from that thing. The shortest distance will always make a right angle. The shortest distance is going to be a right angle. So let me cheat on the right angle. Watch how this works. So here's my point, right? I'm going to use the compass's angle edge to line it up with like an L. So anyone that is interested in drafting or construction, see that this is the L here? So we know that's going to be a right angle. So this is the shortest distance because we know this is a right angle. Did you see how that worked? And so if we do the same thing on the other side, it'll be the same distance. Okay, so from that point, I'm going to line up my compass so I can have my L in here, and I know that's going to be a 90-degree angle. Did you like that cheat? So that's the distance from the point to the side is the shortest possible distance as we've established here. Okay, so hopefully you followed that. If not, that's pretty darn critical knowledge. So right now, if you're listening, as you should, and you don't understand anything that just happened, pause, rewind, and listen carefully as I was talking about this. That is a huge deal, ladies and gentlemen. So the angle bisector theorem says that the distance from the point on the ray to the side, if it's on the angle bisector, is equidistant. Okay? So we can do that again. So pick any random point on the ray, any random point. And if I have the distance from that point to the side, okay, which is going to make a right angle. Hopefully you saw how I cheated there. Okay, and I'll do it again. Let me turn my compass around so I can make my L there. Right? Or T-square, whatever all these tools are you can use in drafting. So anyway, if that's the distance is equidistant, right? And that's the angle bisector theorem, which, if you haven't noticed, will always be true. Why? Because of angle, side, congruence. Review! Full circle. So anyway, those are the notes. Hopefully I explained them a little bit better than, than what you might find in a textbook, but that's the deal. If anybody that was confusing, rewind. Because now we're going to get into algebra for the rest of the lesson. The rest of the lesson is algebra. So now we have this, right? Use the perpendicular bisector theorem. The question is, what's the length of AB? Well, where is AB? And here's AB. How are we going to find that length? What is going to go on? Well, what can we establish from this picture? We look at the diagram, we got to wonder, what is it that we know is going on in this diagram? And hopefully you see that BD is the perpendicular bisector of AC. Perpendicular bisector. Okay? So BD is the perpendicular bisector of AC. Hopefully you can see that. Once you do see that, magic happens. That means any point on BD is equidistant from A and C. But since B is the point on AD, that means from B to A is the same distance from B to C. Okay? BA is the same distance as BC. So all points on BD are equidistant from A and C. Or like I had mentioned before, we can also establish side angle side congruence. And corresponding parts are congruent. But either way, we have to know, we have to be able to establish that AB is equal to CB, okay? So A to B is equal to C to B. And by the way, that's not a typo, okay? I did not leave off a mark. That means the distance from A to B and the distance from C to B, and that is totally equal because distances are equal. Segments are congruent. Distances are equal anyhow. So if we can establish that, game over. That was all the thinking we had to do for this particular problem because now we can do algebra. Yay! Love me some algebra, ladies and gentlemen. So with algebra, what we can establish from that is this equation. Okay, so we have this equation now. 4x is equal to 6x minus 10. So what I'd like to do, let me do this in a screwy way. Here's a common mistake students make and they can't recover from it. So I'm going to make this, it's not really a mistake, but I'm going to do what you normally do and then recover from it. Students will normally look at this and say, I got to get my x's together, and then they subtract 4x from both sides, which is completely legitimate. But then what students do is ruin this, because what they do is something I call losing the equal sign. Never ever lose your equal sign. Your equal sign must be there, right? So you can totally do this. 6x minus 4x is 2x. There's the minus 10. But then you're thinking, what? What goes on here? This is 0, folks. Okay, so 0 is there. 0 is a number. Don't ignore it because it is a number. 0 has feelings. Don't ignore it. Okay, so we have something there. So if you ever make that mistake and you get confused, just remember, never ever lose your equal sign. Because now hopefully you can see I got to separate some stuff. Let me add 10 to both sides. Right? And so now you're seeing hopefully something a bit more comfortable. Right? And so now we can divide by 2. And so x is 5, right? We know that. Now, don't go circling your answer because that wasn't the question. The question wasn't solve for x. The question is, what's the length of AB? How far is it from A to B? It's 4x, but guess what we now know? We now know x is 5. So we're going to have 4 times 5. 4 times 5 is, of course, 20. So the length of AB is 20 units. Okay, but look at all the neat things we had to know. We had to be able to establish that was a perpendicular bisector, establish equality in the segment distances, and then use some algebra. Anyway, I hope that was helpful. Let's do another example. Using the perpendicular bisector theorem again. Now, what is the distance from Q to R? Well, what can we establish in this diagram? Okay, so whenever you're looking at pictures, you got to think, what can we establish in the diagram? Can we establish that QS is the perpendicular bisector of PR? Yes, we can. And if that's the case, then PQ and RQ are equal. Okay, so we have to know that we can establish that. So we can now set up an equation. I don't know why I wrote a 2 there, but anyway, my equation. This is equal to that. Right? So 3n minus 1 is equal to 5n minus 7, and let the algebra begin. Now, in a case like this, where you can choose to undo variables or ones, I like to undo variables first. That's my first order of business. And in this case, be careful. A common mistake is to not call that -1 when it is. And then 5n minus 3n is 2n, and then minus 7. And now I need to solve for n. I got to get rid of that -7, and so I add 7 to both sides. And then read what you have. -1 plus 7 is, of course, 6. Always has been, always will be. And then we have 2 times n. And then to solve for n from 2 times n is divided by 2. And then n is equal to 3, right? Now, before you go circling your answer, again, read the question. The question is, what is QR? So the distance from Q to R, 5n minus 7. But what did we now establish? We established that n is 3. So we're going to plug in 3 for n. And so we have 5 times 3 minus 7, or 15 minus 7, which is otherwise known as 8. Okay? So that is the distance from Q to R. Perpendicular bisector theorem. Yay! Next example, because the notes were the fun part. Now we're going to use perpendicular bisectors. Yay, real world. For all of you interested in theme park management, a park director wants to build a T-shirt stand equidistant from the roller coaster and the spaceship chute. Equidistant. Same distance from a roller coaster and a spaceship chute. What are the possible locations of the stand? Explain. Well, where is the roller coaster? Right? It's right here. And where is the spaceship chute? It's right here. Now, equidistant. Remember, it's same distance from one to the other. And so, where can we put the T-shirt stand? Now, some of you may be thinking, well, that's duh, cats, right? Draw the line from roller coaster to spaceship chute. Equidistant is going to be like right in the middle, you know? Make the perpendicular bisector. Put it in the middle. So just put the midpoint there. But it's actually, that's not the only location. You know, what if there was a sinkhole there or something, right? What if there was another ride there? There's not the only T-shirt stand possible location. It's anything on that bisector. Remember the construction that we made for perpendicular bisector. Equidistant is going to be the same no matter where. If it's on that perpendicular bisector, it's going to be equidistant from the endpoints. We have to remember that. So for the T-shirt stand, it could be anywhere. And watch this cheat. Let's say that's the midpoint, however. Right? We'll cheat. I'm going to cheat. Okay, so it could be anywhere on that perpendicular bisector. So let's just say we have a perpendicular bisector. It's the T-shirt stand is anywhere on that perpendicular bisector. All those possible T-shirt stands. Okay, that's going to be equidistant from the roller coaster to the spaceship. Okay, so what are the possible locations? Anywhere on the perpendicular bisector. Okay, anywhere on the perpendicular bisector. So if you ever encounter that in real world stuff, nothing as straightforward as that will probably happen, but it's possible. So a similar question, right? Suppose the director wants the T-shirt stand to be equidistant. There it is. Equidistant from paddle boats and the spaceship chute. What are your possible locations? Well, where are the paddle boats? Right? Bing. Where's your spaceship chute? Bing. So what's going to be equidistant from both is anything on the perpendicular bisector. Okay? So how do we what if this is real life? You know, how can we establish the perpendicular bisector? Well, if you measure it, right? From there to there is, what is it, about 7.5 centimeters. So what's that? 375. So 3.75 centimeters, about there's the middle. And then just do the perpendicular bisector. You know, cheat on the 90-degree angle. And then make it thin. So here's your bisector. And then we know it's going to be perpendicular. So anywhere on that line. Okay? And that's how we can do this. So what are the possible locations? Anywhere on the perpendicular bisector. Bokeh. Next. I hope we know perpendicular bisectors by now. Let's change our speed into angle bisectors. Yay! Oh, man. More algebra. So what is the length of Rm in this question? Well, here's Rm. what is going on in this diagram? Let's see what we can see. So we look at this diagram and we ask, what is it that we can establish? Are we looking at a bisector? Yeah, dude, check this out. Angle here, congruent angle. What does that mean? That means NR is the angle bisector of LNQ. Okay, that's totally what we can establish, that the ray NR bisects LNQ. Now, what does that mean? Okay, if you remember from our construction example, that means all the points on NR are equidistant from the sides, right? And you remember how we talked about the distance from a line or from a point to a line, right? Makes that 90-degree angle. Remember that? Rewind. Rewind to the beginning of the video. Or we can use angle side congruence, right? So that means basically what this means. MR and PR are the same, right? Dude, that's what that means. And so we have a pretty before you jump into algebra, I'd like you to make sure you can use it first. Okay, so that's why you always ask, what can we establish? Always ask that first before you just jump right into equations, because sometimes you might be solving things that you can't solve, right? You're not allowed to because it ain't true, but in this case it is. So in this case we know NR bisects the angle, which means that MR and PR are the same. MR and PR are the same, right? We can totally establish that. And why can we establish that? Because it's an angle bisector. Why is it an angle bisector? Because rewind, dude, right? So whenever you get stuck, you want to ask why, which is nothing wrong with that. But if you ever do that, just rewind. I'm telling you, I cover my bases. Anyway, algebra. So we have 7x minus 2x is 5x. We know that. We're left with 25. Do I even need to show work anymore? I hope not. So we know in this case x is 5. But that's not the question. The question is find the length of RM, segment RM. Well, where is segment RM? There it is. It's 7x. But we found out what x is. X is 5. 7 times 5 is, of course, 35. And so we know the answer is 35 units. Yay! That's using the angle bisector theorem. Mr. Katz, is there more? Yeah! Let's do another one. What is the length of the segment FB? So it's the same thing happening. Take a look at the diagram and always ask, can we establish anything? We have an angle bisector, which means that every point on the line is the same distance. How do we know we're dealing with distance here? Because we have right angles. We know we're dealing with a distance. Okay, and if that's the case, well then FB and FD are equal. Okay, so bam, we just made up an equation just by looking at it. So we know that 6x plus 3, or BF, is equal to 4x plus 9, or DF, right? We can establish that. So here's an example of another trick for algebra. I got variables going on. I like to undo my smaller one first. So instead of subtracting 6x, I'm going to subtract 4x first, because I like to subtract the smaller coefficient first. Just a little hint, you're welcome. And so I'm left with 2x plus 3 there, and that equals 9. Now I'm going to subtract 3 from both sides. I hope you see that. Boop. And then 2x is going to equal 9 minus 3. I have the right number of fingers, and I can do that on my hands to get 6. So x, of course, is 3. Now don't go circling your answer, right? Because you got to, what's the question? What's the length of the segment FB? So let's look for segment FB. It's 6x plus 3. But we just found x to be 3, so it's 6 times 3 plus 3, otherwise known as 18 plus 3, otherwise known as 21. So we have 21 units is the length of segment FB. Okay? Are we done yet? No, because this is an awesome quiz question. Check this quiz out. I love this question so much. I'm showing you. I'm going to take up a couple more minutes of your time. We're going to use this figure below. Here's this neat, it's a neat question. If segment RT is extended to contain a point W so that UW has a length of 8, what is the length of SW? Now, if you can understand each of those words, that's fine. But if you can understand what happens when you put those words together, that's even better because you can do it in your head. If you've been paying attention to the lesson at all, you should know the answer right now. But if you haven't, let's go bit by bit. If RT is extended, and so we have RT, let's imagine that it's extended, right, to contain a point W, here's a point W, so that UW has a length of 8, so that UW has a length of 8, what is the length of SW? What is the length of SW? Now, you could have totally answered that if you knew all the words. You could have done that in your head. As you can see now, though, we now have a perpendicular bisector. The extension, TW, the extension, is now the perpendicular bisector of SU. That means 8 here, 8 there. When it's such a great question. I want to show you that quick quiz. It's a really cool question. I wish it wasn't multiple choice, but whatever. That's it for today, and I hope you enjoyed it. This was nice and fun. I will talk to you guys later.